Welcome everyone. We will discuss the topic groups. Binary operations. Very often in mathematics, we are interested in combining the elements of some set. We have come across many such examples. As an example, propositions were combined to form new propositions using logical connectives. The operations of union and intersection of sets, as we know, each combine two sets to give a third denoted by A union B and A intersection B respectively. Remember the definition of composition of functions. The essential feature of each of these examples is a rule which allows two members of a specified set to be combined. For our purposes in this section, we shall require that the rule must provide a means of combining any two elements, and the result must itself be a member of the set. A rule which satisfies these criteria is called a binary operation. Of the examples given above, whether or not a particular rule is a binary operation depends critically upon the set in question. For example, addition is a binary operation on the set of positive integers. Any two positive integers can be added and the result is also a positive integer. On the other hand, subtraction is not a binary operation on this set because given any two positive integers m and n, the result m minus n is not always a positive integer. Subtraction is a binary operation on the set of all integers, however. A binary operation on a set A is an everywhere defined function f from A cross A to A. Observe the following properties that a binary operation must satisfy. First one, since domain of f is equal to A cross A, f assigns an element f of AB of A to each ordered pair A comma B in A cross A. That is, the binary operation must be defined for each ordered pair of elements of A. Second one, since a binary operation is a function, only one element of A is assigned to each ordered pair. Thus, we can say that a binary operation is a rule that assigns to each ordered pair of elements of set A a unique element of set A. We will see one example. Let A be the set Z, set of all integers. Define A star B as A plus B. Then star is a binary operation on Z. Another example. Let A be the set R, the set of all real numbers. Define A star B as A by B. Then star is not a binary operation since it is not defined for every ordered pair of elements of A. For example, 3 star 0 is not defined since we cannot divide by the element 0. Example 3. Let A be the power set of set S for some set S. If V and W are subsets of S, define V star W as V union W. Then star is a binary operation on A. Moreover, if we define V star W as V intersection W, then star is another binary operation on A. As example 3 shows, it is possible to define many binary operations on the same set. A binary operation on a finite set may be defined using a table showing the result of applying that operation to any ordered pair of elements of the set. For example, if S is the set A, B, C, D, we can define a binary operation star on S by the table shown. The convention for interpreting the table is that B star D, for example, is defined to be the element at the intersection of the row labeled B and the column headed by D, so that B star D is equal to B. Similarly, C star D is equal to A, D star C is equal to C, C star C is equal to A, and so on. A table which defines a binary operation in this way is called a Cayley table. Properties of binary operations. A binary operation on a set A is said to be commutative if A star B is equal to B star A for all elements A and B in A. An example, the binary operation of addition on Z is commutative. The binary operation of subtraction on Z is not commutative since 2 minus 3 is not equal to 3 minus 2. A binary operation star on a set A is said to be associative if A star B star C is equal to A star B star C for all elements A, B and C in A. The binary operation of addition on Z is associative. Algebraic structures. An algebraic structure consists of one or more sets together with one or more operations which enable members of the sets to be combined in some way. What is important about a particular algebraic structure is that many of its properties are predictable from the characteristics of the operation or operations involved. This means that we can classify algebraic structures into families whose members have many features in common. Identification of a given algebraic structure as belonging to a particular family of structures allows us to conclude that it has the properties which are the characteristics of all members of the family. Semigroups. In this section, we will define simple algebraic structure consisting of a set together with a binary operation that has many important applications. Definition. A semigroup is a non-empty set S together with an associative binary operation star defined on S. We shall denote the semigroup by the pair S comma star, or when it is clear that the operation star is simply by S. We also refer A star B as the product of A and B. The semigroup S comma star is said to be commutative if star is a commutative operation. An example, the set power set of S where S is a set together with the operation of union is a commutative semigroup. Example 1, the set Z with the binary operation plus is a commutative semigroup. Another example, let S be a fixed non-empty set and let S raised to S be the set of all functions f from S to S. If f and g are elements of S raised to S, we define f star g as f composition g, the composite function. Then star is a binary operation on S raised to S and star is associative. Hence, the pair S raised to S comma star is a semigroup. The semigroup S raised to S is not commutative. An element E in the semigroup S star is called an identity element if E star A is equal to A star E is equal to A for all A in S. We have a theorem which says an identity element must be unique. Example, the number 0 is an identity in the semigroup Z with binary operation plus. Another example, the semigroup Z plus with binary operation plus, where Z plus is the set of all positive integers, has no identity element. Theorem, if E is an identity for a binary operation star, then E is unique. Proof, assume another object I also has the identity property, so X star I is equal to I star X is equal to X. Then E star I is equal to E. But since E is an identity for star, I star E is equal to E star I is equal to I. Thus, I is equal to E. There is at most one object with the identity property. Definition, a monoid is a semigroup S comma star that has an identity. Example, the semigroup, the power set of S has the identity empty set, since empty set union A is equal to empty set, which is equal to A union empty set for any element A in power set of S. Hence, power set of S is a monoid. Example, the semigroup S raised to S we defined has the identity 1 raised to S since 1s composite F is equal to F composite 1s for any element F element of S raised to S is a monoid. Let S comma star be a semigroup and let T be a subset of set S. If T is closed under the operation star, that is A star B is an element of T whenever A and B are elements of T, then the pair T with the operation star is called a sub-semigroup of S star. Similarly, let S star be a monoid with identity E and let T be a non-empty subset of S. If T is closed under the operation star and E is an element of T, then the pair T with the binary operation star is called a submonoid of S star. Observe that the associative property holds in any subset of a semigroup, so that a sub-semigroup T star of a semigroup S star is itself a semigroup. Similarly, a submonoid of a monoid is itself a monoid. Now we come to the topic groups. The term group was coined by Galois about 150 years ago to describe sets of one-to-one functions on finite sets that could be grouped together to form a closed set. As is the case with most fundamental concepts in mathematics, the modern definition of a group that follows is the result of a long evolutionary process. Although this definition was given by both Heinrich Weber and Walther von Dijk in 1882, it did not gain universal acceptance until this century. In this section, we examine a special type of monoid called a group that has applications in every area where symmetry occurs. Application of groups can be found in mathematics, physics and chemistry, as well as in less obvious areas such as sociology. Recent and exciting applications of group theory have arisen in fields such as particle physics and in the solution of puzzles such as Rubik's Cube. Definition: a group, the ordered pair G with an operation star, is a monoid with identity element E that has the additional property that for every element A in G, there exists an element A dash in G such that A star A dash is equal to A dash star A is equal to E. Thus, a group is a set G together with the binary operation star on G such that A star B star C is equal to A star B star C for any elements A, B, C in G, which is the associative property. There is a unique element E in G such that A star E is equal to E star A for any A in G, which is the existence of identity. For every A in G, there is an element A dash in G called an inverse of A such that A star A dash is equal to A dash star A is equal to E, which is the existence of inverse. Observe that if the pair G star is a group, then star is a binary operation, so G must be closed under star, that is A star B is an element of G for any elements A and B in G. To simplify our notation, from now on, when only one group G star is under consideration and there is no possibility of confusion, we shall write the product A star B of the elements A and B in the group G star simply as AB, and we shall also refer to the group G star simply as G. We also define powers of X as follows. If n is an element of Z plus, x raised to n is equal to x star etc. x n times, and if n is an element of Z minus, x raised to n is equal to x raised to minus 1 raised to mod n, which is equal to x raised to minus 1 star x raised to minus 1 star etc. star x raised to minus 1 mod n times. Definition: a group G is said to be abelian if AB is equal to BA for all elements A and B in G. Example: the set of all integers Z with the operation of ordinary addition is an abelian group. If A is an element of Z, then an inverse of A is its negative minus A. Example: the set Z plus under the operation of ordinary multiplication is not a group since the element 2 in Z plus has no inverse. However, this set together with the given operation is a monoid. Next example, let G be the set of all non-zero real numbers and let A star B is equal to AB by 2. Show that G star is an abelian group. Solution: we first verify that star is a binary operation. If A and B are the elements of G, then AB by 2 is a non-zero real number and hence is in G. We next verify associativity. Since A star B star C is equal to AB by 2 star C, which is equal to ABC by 4, and A star B star C is equal to A star BC by 2, which is equal to ABC by 4, the operation star is associative. Let E be the identity in G, then E star A is equal to EA by 2, which is equal to AE by 2, which is equal to A star E is equal to A. This shows that E is equal to 2. Finally, A dash is an element of G, be the inverse of A. Then by definition, A star A dash is equal to A dash by 2, which is equal to E, which is equal to 2, gives A dash is equal to 4 by A. Thus 4 by A is an inverse of A. Since A star B is equal to B star A for all A and B in G, we conclude that G is an abelian group. Next example. For each positive integer m, the set Zm of congruence classes of integers modulo m, denoted by plus subscript m, is a group, where the group operation is addition of congruence classes. For Zm is the set of classes generated by 0, 1, 2, etc. m minus 1. The table for addition modulo 5 is shown in the screen. So in the table you can see operation addition modulo 5 on the numbers 0, 1, 2, 3, 4. For example, 2 addition modulo 5 2 is 4. That means the remainder obtained by dividing 2 plus 2 is 4. Similarly, the remainder obtained by adding 4 plus 1 is 0. Clearly, 0 is the identity element. It is an abelian group. Next definition. The order of a group G star is a cardinality of the set G, and it is denoted by mod G. Next definition. The order of an element G in a group G is the smallest positive integer n such that G raised to n is equal to E. In additive notation, this would be n into G is equal to E. If no such integer exists, we say G has infinite order. The order of an element G is denoted by mod G. For example, consider the set of all integers Z. Here every non-zero element has infinite order, since a sequence A, 2A, 3A, etc. never includes 0 when A is not equal to 0. Properties of a group. Theorem. Uniqueness of the identity. In a group G, there is only one identity element. Proof. Suppose both E and E dash are identities of G, then A E is equal to A for all A in G and E dash A is equal to A for all A in G. The choice of A is equal to E dash in 1 and A equal to E in 2 yields E dash E is equal to E dash and E dash E is equal to E. Thus E and E dash are both equal to E dash E and so are equal to each other. Next theorem is the theorem on cancellation. In a group G, the right and left cancellation laws hold. That is, BA is equal to CA implies B equal to C and AB equal to AC implies B equal to C. Proof. Suppose BA is equal to CA. Let A dash be an inverse of A. Then multiplying on the right by A dash gives BA into A dash is equal to CA into A dash. Associativity yields B into A dash is equal to C into A dash. Then BE is equal to CE and therefore B equal to C as desired. Similarly, one can prove AB equal to AC implies B equal to C by multiplying on A dash on the left side. Next theorem on uniqueness of inverses. For any element A in G, the inverse is unique. Proof. Suppose B and C are both inverses of A. Then AB equal to E and AC equal to E by definition. So that AB equal to AC. Now using cancellation law, we can cancel A. Thus B is equal to C. These cancellation laws, as they apply to addition and multiplication of non-zero real numbers, are a familiar feature of elementary algebra. The next theorem also has a familiar application in elementary algebra. The linear equations A plus x is equal to B and Ax is equal to B have unique solutions for x as long as A is not equal to 0. The need to solve equations such as these arises frequently, and we might therefore ask, given a binary operation star, under what circumstances does the linear equation A star x is equal to B have a unique solution? For the members of the group, however, we can prove that every such equation has a unique solution. Theorem. If G star is a group and A and B are elements of G, then first one, the equation Ax is equal to B has a unique solution x is equal to A inverse B, and second one, the equation Ya is equal to B has a unique solution y equal to B into A inverse. proof. For the first one, suppose we have Ax is equal to B. Pre-multiplying this equation by A inverse gives A inverse Ax is equal to A inverse B, implies A inverse A into x is equal to A inverse B, which is equal to Ex is equal to A inverse B. That is, x is equal to A inverse B. Thus, x is equal to A inverse B is a solution of the equation. We must now show that this is the only solution. Suppose that x1 and x2 are both solutions of Ax is equal to B. Then we have Ax1 is equal to Ax2, which implies x1 equal to x2 by left cancellation law. Hence, x is equal to A inverse B is the unique solution. The proof of the second one is similar. A useful consequence of each of these two theorems is their implication for the Cayley table of a group G star with a finite number of elements. The second theorem guarantees that every element appears exactly once in every row and column. To see why this is so, consider an arbitrary element A in G. Any element G in G appears in the row corresponding to A if the equation Ax is equal to G has a solution for some x in G. In this case, G is in the column corresponding to x as shown in figure. Theorem states that this equation has a unique solution for each G element of G. Hence, every element of G appears just once in the row corresponding to the element A, and since A was chosen arbitrarily, we can deduce that every element of G appears exactly once in every row. A similar argument can be used to show that each element appears exactly once in every column. Definition: a group G star is said to be cyclic if there exists an element A in G such that for each element G in G, G is equal to A raised to n for some n element of Z. The group G star is said to be generated by A, and A is called the generator of the group G star. In the notation for an additive group, one where the binary operation is addition, the element A is a generator if for all G in G, G is equal to n into A for some integer n. A cyclic group is necessarily abelian because given G1 and G2 in G, we have G1 is equal to A raised to R and G2 is equal to A raised to S for some R and S in Z, so that G1 G2 is equal to A raised to R into A raised to S, which is equal to A raised to R plus S, which is equal to A raised to S plus R, which is equal to G2 into G1. An example: show that the group Z with the operation plus is cyclic with the generator 1. Solution: the identity element is 0 and the inverse of the element 1 is minus 1. For any element n in Z where n is greater than 0, we have n is equal to 1 plus etc. plus 1 n times, which is equal to n into 1. If n is less than 0, n is equal to minus 1 plus etc. minus 1 mod n times, which is equal to mod n into minus 1, which is equal to n into 1. If n equal to 0, then n equal to 0 into 1, which is equal to n into 1. Hence, Z with the binary operation plus is a cyclic group and 1 is a generator. A similar line of argument will show that minus 1 is also a generator of the group. Now let us summarize what we have learned in this session. We have learned a binary operation, we have studied the concept of semi-groups, monoid and groups. Examples were given to illustrate and distinguish these concepts. Properties of groups were proved. Then the concept of order of a group was explained and different types of groups were presented. More problems were discussed to understand these structures. The following are some assignment problems. First one, consider the binary operation of subtraction on the set of real numbers. Is this operation associative, commutative, and does an identity element exist, and if so, which elements have inverses? Second problem, show that the set of all 2 by 2 matrices with real elements together with the binary operation of matrix addition is a group. Why is this set together with matrix multiplication not a group? Third one, show that matrix multiplication on the set of all 2 by 2 non-singular matrices is a binary operation. Also prove that the set forms a group under matrix multiplication. Next problem, if star is a binary operation on a set S, then an element x in S is said to be idempotent if x star x is equal to x. Prove that a group has only one idempotent element. Fifth problem. Let P be the set P element of Z plus such that P is prime and P is less than or equal to 13. A binary operation star is defined on P by P star Q is equal to greatest prime divisor of P plus Q minus 2. Construct a Cayley table for P under the operation star and show that P has an identity element with respect to star. Is P with the operation star a group? Justify your answer. Next problem. Show that for any group G star, AB the whole inverse is equal to B inverse A inverse for all AB element of G. Deduce that if A is an element of G, then A inverse into N is equal to A raised to N the whole inverse into 1 for all N in N. Next problem. Prove that a cyclic group with only one generator cannot have more than 2 elements. Now we will see some reference books. First one is the Elements of Discrete Mathematics, 2nd edition by C.L. Liu, McGraw-Hill International Edition, Computer Science Series 1986. Second one is Concrete Mathematics, A Foundation for Computer Science by Ronald Graham, Donald Knuth and Oren Patashik in 1989 by Edison Wesley. Third book is Mathematical Structures for Computer Science by Judith L. Gersting, 1993, Computer Science Press. Fourth one, Applied Discrete Structures for Computer Science, Dorr and Levasier, Chicago, 1985, SRA. Fifth one, Discrete Mathematical Structures by Coleman and Busby in 1996 by Prentice Hall, International Edition. Discrete Mathematical Structures with Applications to Computers by Tembley and Manohar in 1995 by McGraw-Hill. Hope you have followed the session. We'll meet in another session with another topic. Till then, goodbye.